All right, well, welcome back. We're now looking at section 2.2, Modular Arithmetic. Now, what we've been focusing on is these congruence classes in Z mod n. So, what we're really trying to do with this idea of Z mod n, you know that with Z mod n, the congruence classes are going to be 0, 1, 2, all the way up to n minus 1. And again, from last lecture, we also talked about why. Because when you divide by n, it's the remainder, which you can get with divide by n. You can get no remainder, 1, 2, 3, all the way up to n minus 1. But you can't have an n remainder when you're dividing by n. So it creates these what we call equivalence classes. Now what we're talking about here with this modular arithmetic is how to actually do the algebraic structure of Z mod n, which means we're going to talk about adding and multiplying and how to put that stuff together to show algebraic structure. So, definition. In Z mod n, where n is an integer and n is greater than 0, we have this. If you're going to take equivalence class A and add it, and we use a fancy way of adding it, plus with a circle around it, equivalence class A plus equivalence class C, that would be equal to, pretty much you make one big equivalence class just to multiply A times C. Now remember, if you get bigger than n, you're going to have to boomerang him back and figure out what he's equivalent to by dividing it by n. Remember, the equivalence classes are always the remainder. But this is how you add equivalence classes. Equivalence class A plus equivalence class C is equal to equivalence class A plus C. And multiplication, equivalence class A times equivalence class C, special way of multiplying, circle dot there. Equivalence class A times equivalence class C is equal to equivalence class of A times C. So in theorem 2.6, we talk about how this structure is actually set up in terms of these guys truly are equivalence classes, and therefore we have that classic structure. So if equivalence class A equals equivalence class B, and equivalence class C is equal to equivalence class B in Z mod n, then equivalence class A plus C is going to be equal to equivalence class B plus D, and equivalence class A times C is equal to the equivalence class of B times D. How we add and how we multiply. Now, what we're going to be looking at is pretty much addition and multiplication of Zn and looking for algebraic structure. Now, when you were in the, 4th grade, 3rd grade, 2nd grade, something like that, you may have done addition and multiplication tables. And that's kind of what we're going to be doing with this stuff. So, I'll turn my page here. I've got a couple, and I made mine very small so I can put them on a sheet of paper so I can show you guys some of these interesting videos that I'm making at home. We're going to do an addition table and a multiplication table for Z4. And after that, I decided to cruise it up one. And I've also got an addition table for Z5 and a multiplication table for Z5. So let's go ahead and look at these guys here. Now, remember, in Z4, the equivalence classes are 0, 1, 2, 3. And that's it. These are the remainders that you could possibly have when dividing it by 4. And so let's create this, quote, addition table. Well, 0 plus 0 is 0. And we put little pointy brackets around to let you know we're still equivalence classes. 0 plus 1 is 1. 0 plus 2 is 2. And 0 plus 3 is 3. 0 plus 3 is 3. And this is how, from the addition way of manipulating equivalence classes, of how we add them. Later on, I'll be doing the multiplication. Now, 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. But here we go. What is 1 plus 3? That's 4, but in Z4 you don't have 4. 4 is equivalent back to 0. Because 4 divided by 4 is 1 with no remainder. So this would be back to 0. Equivalence class 4 would now be back to equivalence class 0. Now 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4, but 4 was equivalence class 0. 2 plus 3 is 5, but equivalence class 5 in Z4 would be back to 1. And 3 plus 0 is 3. 3 plus 1 is 4, but in Z4 that's 0. 3 plus 2 is 5, but 5 would be equal to 1 in Z4. And 3 plus 3 is 6. 6, when you're doing Z4, when you divide by 6, you get a remainder of 2. So it's equal to the equivalence class 2. So this is your addition table for Z4. The multiplication table for Z4, again, done similarly, except you multiply the numbers and put a big pointed bracket around them. 0 times 0 is 0. 0 times 1 is 0. 0 times 2 is 0. And 0 times 3 is equal to 0. 1 times anybody is anybody, so 1 times 0 is 0. 1 times 1 is 1. 1 times 2 is 2. And 1 times 3 is 3. So let's go beyond that. That's where it gets more interesting. What is 2 times 0? Well, that's still 0. 2 times 1 is 2. 2 times 2 is 4, but in Z4, that's equivalent to 0. And 2 times 3 is 6, but 6 in Z4 is back to 2. You can keep subtracting off multiples of 4 until you get a number between 0 and n minus 1. Or you can divide, and the remainder you get would be your equivalence class. Or you can just keep subtracting them off until you get a number between 0 and n minus 1. So 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. But 6 in Z4 would be 2. And then, last but not least, 3 times 3 is 9. But in Z4, you keep subtracting all multiples of 4. 9 minus 4 is 5. 5 minus 4 is 1. And there's your multiplication table. And what this also means is, with this, understanding the tables, we can create a lot of algebraic structure in solving for algebra or solve for X on particular problems. But I want you to compare the relationship between Z4 and bumping it up one more in Z5. So Z5, the equivalence classes are going to be from 0 through 4. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. But they are equivalence classes, so you need to put the little pointed brackets around. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. Remember, we're in Z5. And 1 plus 4 is 5, but in Z5, that's equivalent to 0. And again, I put pointed brackets around to denote the fact that these are equivalence classes. 2 times 0 is, 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, but 5 is equivalent to 0. And 2 plus 4 is 6, and Z5, 6 is equivalent to 1. And then the last row, actually 2 more rows, as we're in Z5. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5, but in Z5, 5 is equivalent to 0. 3 plus 3 is 6. In Z5, that's 1. 3 plus 4 is 7. And 7, subtract off multiples of 5, or in this case just 1 5, you get 2. And then 4. 4 plus 0 is 4. 4 plus 1 is 5, but in Z5, 5 is equivalent to 0. 4 plus 2 is 6, 6 is equivalent to 1. 4 plus 3 is 7, 7 is equivalent to 2. And 4 plus 4 is 8, and 8 in Z5 would be 3. And there's my multiplication table for Z5. addition table for Z5. Now we're going to move on to the multiplication table. And again, that gets a little more interesting here. 0 times 0 is 0, 0 times 1 is 0, 0 times 2 is 0, 0 times 3 is 0, and 0 times 4 is 0. And these are equivalence classes. 1 times 0 is 0, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4. 2 times 0 is 2, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, but we're in Z5, so that's equivalent to 1, and 2 times 4 is 8, and Z5 that's equivalent to 3. Three times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, but in Z5, 6 is equivalent to 1. 3 times 3 is 9, and Z5, that would be 4. And 3 times 4 is 12, and in Z5, subtract off from a couple of 5s, multiples of 5, that would be subtract off 10, and I get 2. And then 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, but in Z5 that's 3, 4 times 3, 4 times 3 is 12, but in Z5 that's equivalent to, subtract off a couple of 5s, you get 2, and last but not least, 4 times 4 is 16, however in Z5, 5 written out, like I said, 4 times 4 is 16, but in Z5, subtract off a multiples of 5, or subtract off 3 times 5, which is 15, you're left with 1. And this is your multiplication tables. And you go, well, why is this important? Well, I could also ask you the question, 3x plus 5 equals 7. Solve for x if I am in Z5. And so you manipulate it until you try to solve for x, and that's when your multiplication table is going to be very helpful in terms of picking out which is my right guy. Now, in this next part, we're going to be looking at properties of the integers, the classic integers, and compare those to actually the properties of Zn. So, here's the property of integers. And again, this is also terminology. We expect you guys to have this stuff memorized at the end of the day and need to know this stuff as we go back and remind you of the fancy definitions. So, if A and B are integers, Z is transfer integers here, then A plus B is an integer. That's called closure under addition, because we're trying to take two elements and we're going to add them, and they're still back inside my set, which is the integers. That's called closure under addition. A plus B plus C is the same thing as A plus B plus C. Moving the parentheses around, that's called associativity under the addition law. A plus B equals B plus A, that is the commutative ring property. Okay, they commute. A plus B and B plus A are the same thing. Additive inverse is a little bit different in the way we write it up in Dr. Hungerford's book. Okay, there exists a 0 in Z such that A plus 0 equals 0 plus A for all A and Z. Now, for the inverse, that's called the additive inverse. For the multiplication type thing here, we have this. See, the additive identity is 0. It's the additive inverse. For each equation, A element of Z, the equation A plus X equals 0. Okay, I know. To solve for X, you would subtract A. But we're working off these interesting rings that we're trying to develop, and now the latest one is Z mod N. I didn't see any negatives around Z mod N, so, that's going to be a problem. But that's why Dr. Hungerford writes the equation A plus X equals 0. So when you solve it, it's negative A. That's your additive inverse. If A is in your set, negative A better be inside your set. Keep going. If A and B are integers, then A times B is an integer. That's called closure under the multiplication property there. A times B plus B times C is equal to A times B times C. Well, here all I did was just move the parentheses around. That's called associativity. For this time it's under the multiplication. If A times B plus C is equal to AB plus AC, and B plus C times A is equal to AB plus AC. That's called the distributive property. A times B is equal to B times A. That's called the commutativity property under a multiplication. 1 is an element of Z, such that A times 1 equals 1 times A, which is A, for all integers A and Z. And that's called the multiplicative identity. And then if A times B equals 0, then either A equals 0 or B equals 0. Now that's actually a fancy property that deals with ideal theory and the like. We'll get to that later. But the idea if a product of two things is equal to 0, does the first guy or the second guy have to be equal to 0? Now, what I'm trying to do here is we have another theorem. It should be here at the bottom here. Theorem 2.7. For all equivalence classes A, B, and C and Zn, we're going to have something similar. And I'm just going to check them off because that means all you have to do is just take this thing and put pointy brackets around them and stuff to make them proper. Well, do we have closure? We've taken two equivalence classes in Z mod n. Yes, we do. Okay, so looking at the properties of integers, now we're talking about the properties for Z mod n. So we're going to have the same thing going on here. For Z mod n, we have closure. If equivalence class A and B are in Z mod n, is that going to be equivalence class A plus equivalent class B is going to be in Zn? Yes, it is. What about associativity? Can I move the parentheses around when I'm dealing with equivalence classes in Z mod n? Yes, you can. What about commutativity? At A plus B equals B plus A? Absolutely. It doesn't matter what equivalence classes, so that's what the property would also hold. Is there a zero equivalence class? Yeah, we put the little pointy brackets around it, and that'll be in Z mod n, such that when I take an equivalence class and add 0, I will get the exact same thing, which is equal to A on both sides there. For any equivalence class A and Z, the equation A plus X equals 0, yep, it's going to have a solution in Zn. Basically, it's the negative equivalence class, and you have to kind of add n back to it to figure out who that guy is going to be, so that's going to hold. And so you'll notice that all these properties of integers is the same thing for the properties of Z mod n, except for one. Let me show you. Here, if A and B are in Z, what about the multiplication of the two guys? So they're going to be in Z. Now we're talking about this being Z mod n now. And yes, we have closure with equivalence classes. So this property also holds for Z mod n. The associativity under multiplication, it doesn't matter if you got three equivalence classes, doesn't matter what order you multiply them out, that holds. We can distribute the front or distribute the back, so that holds. We have commutativity. So if equivalence class A times B is equal to equivalence class B times equivalence class A, doesn't matter what order you're going to do them because you're going to multiply them anyway. Is there a one equivalence class? So when I multiply any equivalence class times 1, I get the other guy back again? Yes, there is. However, this property right here of integers, if A times B is equal to 0, then does that force that A have to be equal to 0 or B has to be equal to 0? Not necessarily. This is the one property that fails when you've got Z mod n. An example of that is us looking over here in Z4. Notice the 2 equivalence class. Equivalence class 2 times equivalence class 2, in this case, is equivalence class 0. 2 non-zero elements multiplied together, it gives me 0. That is not what we have here. According to the property with integers, if I ever have a product equals 0, then either the first dude had to be 0 or the second dude had to be equal to 0. So Z mod n has pretty much the same structure as the integers, except property number 11. The idea of any time I have a product equals 0, then the first guy has to be equal to 0 or the second guy has to be equal to 0? Not necessarily. Okay? So this is the end of section 2.2. And again, we're talking about the algebraic structure and how to manipulate them. Basically, we're going to be looking at equations in Z mod n and how to solve these guys.